Thank you, Verena, you flattered me. But it's a great pleasure to give this talk and an honor at the Cogwiz conference. So let's delve right in. Geoscience relation, one word to this. Why? Because for a long time I was working on spatiotemporal cognition and how we perceive and interact with space over time. And that's really spatiotemporal dynamics. We use some techniques there and translated that to the geoscience predictions. But today I want to focus on a topic that has really boggled me now for the last couple of years, as Verena already said, and this is the apparent fact that our minds continuously contextualize what we are thinking about. So really the focus of our minds is not really everything all the time, as we well know, but it's also not the attention that we just really look at right now, but it's kind of the frame within our behavior and our attention unfolds. And this is all what this talk is about. So what I want to emphasize first, so which context am I really talking about? And clearly context is all around us, right? When we sit on the laptop with a coffee or what, it's of course the laptop and the coffee and the table that sets the context for us. But there is so many details around us, and lots of cognitive science research has shown to us that we don't perceive everything around us, we don't process everything around us, right? Good examples of this is, for example, change blindness, right? Where we think we see a full scene, but we don't notice, or it takes us quite a while to notice an important detail. Here it's the line on the street, yeah, that is just slips our conscious attention, but when we see it, it's suddenly there, and it's incredible that we haven't seen it. Yeah, and others have shown in related work inattentional blindness, right? That we are, when we count the basketball passes of the white team, we are so in the counting routine and tracking this white team that passes the ball, yeah, and we're very good in counting those basketball passes, and we think we see everything in the scene, and we totally overlook the gorilla that has passed through. And most of you know these experiments, right? So I will not show it to you again. But it shows nicely, right, that yes, context is around us, right, and in all of us, right? It's always the environment gives us the context, but really we don't perceive this whole context. Yeah, we only perceive and focus a part of this environmental context that seems relevant to us, and this context that we look into is rather abstract. Yeah? It's not the details of the environment that the environment really provides to us. So it's rather abstract and rather conceptualized. So the proposal that I've been following over the last years is really that, well, our minds seem to actively contextualize, but what does this really mean, right? This is the big question that I want to address in this talk. And I want to give you a couple of further illustrations of this. Here, a nice Escher artwork picture that illustrates how context determines what we deem foreground and what we deem background at any point in time. Right? And so we can only see the reddish, orangish horse riders or the gray ones really, and can focus on them, and the other one is in the background. Right? It's the context that determines what is foreground, what is background, and this is not determined by the environment, but our mind decides what is currently foreground and what is background. Yeah? If you look at this Escher picture, which he called Three Worlds, is nicely showing to us that also here we have three different contexts. We have the fish under the water, yeah? And so if we perceive the fish under the water, it's the underwater context that we have in our mind, and then we can explore within that context. And we have a really hard time to meanwhile perceive the surface of the water and see the leaves on the water. Yeah? So to count the leaves on the water, if you count the leaves on the water, it's nearly impossible to, in parallel, imagine the fish swimming below the water and inside the water. Yeah? In the third world, are the trees and the shadows of the trees. And if we perceive the 3D shadows of the trees and want to explore the trees, we cannot really focus on the fish or the surface of the water. So environments offer context, but we decide which part of the environment, what is the contextual frame that we want to look into and that we want to explore further. And this contextual frame needs to be somewhat consistent in our minds. Yeah? We want to have a consistent contextual frame within which we think. If we have this artwork, we have local context. Yeah? This person looking up, this person taking up a ladder, but then you see up here, well, this person looking down, but meanwhile, they're standing on the ground, and you have the impression that this terrace here goes into the depth, right? And so what does your mind do? It tries to integrate all this local context if you want to have a global picture of the scene, and so the terrace kind of bends in your head because that's the best explanation that you can come up with. Yeah? Another nice one is this fun illustration of a woman standing on a flying carpet, which is obviously not a flying carpet, but again, the shadow situation, the coincidence of this flag shadow here, actually, right? This flag, the coincidence that this matches so well with this mat, it basically seems to be, for us, it must be a shadow, and the light situation is such that basically the shadow can only be created if it was above the ground in such a way. And that's what our mind puts together. And if you take the shadow away, we more or less put the woman back onto the floor because there's no illusion anymore, but still a little bit of an after effect, of course. So we enforce consistency, and of course, this whole thing is like task-oriented. I take this scene as a last main example that I want to show, this Wimmel kind of built scene with various things happening. If you see the overall scene, okay, some scene with lots of people moving around and so forth. But if I give you a task and basically say, well, count the number of, say, the flying birds. Yeah? So then you zoom into a particular contextual subframe, which is the air, and what can be flying around, and you detect some birds, and maybe you detect a couple of more, right? And so that was your air context kind of, that you see, okay, it's flying birds, must be in the air. If you follow me and you swap your attention and you say, okay, count the number of deer, so look at the number of deer, so basically suddenly you get into this background scene here, and you have a little picturesque scene of the deer, and it's the deers that matter to you, and everything else is more or less out of attention, and you can roam around with the deer. And we can play this more, right, as shepherd content, and so we look at the shepherd. Is there a black sheep? So then you look at the sheep scene, right, and you suddenly have again your contextual frame within which you think. And if we continue, last one, the water lilies in the pond, suddenly you notice the pond and you explore the pond and can see how they are doing, or which photograph is taken. Where's the photograph? Here, so there's a scene with the photographer, right? And so each time, right, you zoom into a different context and you keep it stable to explore the content of this local context that you are currently interested in a task-oriented manner. So what I really want to imply with this, right, is that it seems that we attempt continuously to infer consistent contextual frames endogenously in our heads, yeah, in a task-oriented manner. And when we have this contextual frame, then we think within this frame. We perceive and analyze the situation. We plan and reason in the frame. We make decisions. We focus on particular aspects of it, and we control then behavior. And there's lots of evidence over the last years, which I don't want to go in detail. We have written a review about this last year, also from the neuroscience and from the developmental side, but also from the cognitive modeling side. But without further ado, I would like to proceed with really not the details of these other studies, but a couple of more intuition about what I'm talking about. So basically, when we follow this proposal, the big question, I think, or two big questions that are really about this contextual framing is basically why and how. Yeah? So why do we do this contextual framing, and how does the mind really do this effectively and seamlessly? And the why question I like to answer with basically, it's an old question in cognitive science. The why question is really tackling the frame problem, or facing the frame problem. That's maybe evolutionary solution to the frame problem is basically that, well, we need to be able to make decisions on the basis of what is relevant to an ongoing situation without having to explicitly consider all that is not relevant. Yeah? That's essentially the frame problem. Yeah? In principle, how do we know what is not relevant without thinking about each of every one of it that might be relevant to us? Somehow we have this intuition that for this particular task only this stuff is relevant. Yeah, if I want to drink out of a bottle, suddenly only the bottle is relevant, and I need to open it and so forth, and the rest, where I'm around it, just to drink out of the bottle, everything else is irrelevant. We know this intuitively all the time. We solve the frame problem all the time. Yeah, or if I term this in contextual framing, that is basically, well, how do we largely effortlessly infer the contextual frame within which our current thoughts unfold, within which we solve our tasks, within which we successfully behave? That's the big question. And the proposal is essentially, well, it seems that active contextual frame inference, so this active contextualizing, has naturally evolved to overcome this ubiquitous frame problem. This frame problem is ubiquitous in our world. Yeah? And why? Because contextual frame inference enables us to focus our planning, reasoning, and decision-making on the task at hand in this contextual frame. We can ignore so much else that we all know, right? We have humongous amounts of knowledge in our heads, right? But if I want to drink out of the bottle, I don't need to think about Plato or how I drive my bike. Yeah, it's unnecessary. Yeah? So it enables essentially faster as well as much more flexible decision-making, faster because I don't need to consider all this other stuff, and more flexible since I can focus on the stuff that's relevant. I can plan through it in much more depth than if I would need to consider all this stuff that is not relevant. So effectively, it's also a very big promise if we implement something like this in deep learning systems and in artificial systems, that it has a very potential to save a lot of energy. Yeah, because we can have much more compact representations and need less extreme planning and so forth. So this was conceptually now first work that shows that this has some merit. What I'm talking about is basically working with my PhD student Max Mittenbühler, who's in the S right now, essentially minimizing as upper bound of surprise in a contextualized graphical model that leads to the emergence of automatic response tendencies and meta control. The study essentially models a large variety of choice reaction time experiments, switch tasks and task switching experiments, and similar. I will just illustrate it along the Stroop task, which I also showed on Monday. Sorry for those that were on Monday. But basically, so right, you get a stimulus like blue written in red, and you have to respond that it's red. Sometimes you press buttons when you have to verbalize it, and it's even harder to say red when you read blue, obviously. So you have congruent and incongruent trials. Congruent trials would be when the word would read red as well and be written in red, and in this case it's an incongruent trial. So we modeled this now with a contextualizing framework. Now the contextualizing framework we give for now, and it's basically a contextual framework that simulates the task decision-making process by a simple graphical model that has basically an estimation of what's the stimulus that I currently observe, what action should I execute, and which result this action will have, so if it will be the correct or the incorrect response, thus if my resulting observation will be that I did it correct or incorrectly. And the context essentially sets prior conditional probabilities on my alpha, on my reactive behavior, given stimulus. What will be my reaction to that stimulus? So essentially read blue, say blue, for example. Yeah? Or just a uniform if I don't want to be biased by my habits. Beta saying, okay, what's the task? So should I read out the word or should I say the color of the word? When will it be correct? That's what beta essentially encodes, given S and A, right, in my response. And then gamma is the resulting observation that I observe. Or also, C can also set the gamma basically as that value that I want to observe. So how much is it important to me that I observe that I was correct when I set the answer? And with this goal-directed observation, with this outcome priority as a gamma, basically I have the task focus defined also in an information theoretic sense. All these nodes, right, are spatial nodes, so it's basically 1, 2, 3-dimensional nodes that are belief states essentially of what I observe, what's my action, what's the consequence, belief densities over these small spaces here. Yeah? And so when I have now this contextual frame, how does decision making then unfold? First, I have, well, when I start with the next trial, my alpha, beta, gammas, and also the epsilon, my priors on the observations that I have possibly, basically say, okay, now I'm ready to do the task. Yeah? Now I fully prepared to only process those stimuli, observe, is it the red color or the blue color, yeah? And I try to ignore the writing, maybe, yeah, to a certain extent. And then I need to choose my response, right? So what I need to do is essentially, well, I need to see which action leads to the correct behavior, dependent how important it is to me to really do the correct behavior. If I don't care, right, I would just press, right? So no effort, don't care, and doesn't matter. That would be just the gamma being like uniform, then okay. Yeah? But if the gamma is peaked to do it well, yeah, and then I want to do it well, and so I basically do a prospective rollouts and making essentially a Markov chain Monte Carlo sampling process that leads me to my actual decision making, my posterior overactions. And then I can use the context activity, the result, and do the context activity retrospectively to optimize my context. And finally, on the long term, integrating over many, many experiences in my life, I basically build my long-term contextual priors and contextual structures. In this experiment and in this model, basically, I will now show you one equation that basically shows how this is really done in the model now. And this model is this equation is essentially the loss, yeah, or the objective function that is fully defined just out of the principle of minimizing surprise over time in that model. Yeah? And within a particular trial, so when I say the context is given and alpha, beta, gamma, and epsilon are set, my trial-specific loss consists of two components if I want to minimize surprise overall. The first component is essentially the log likelihood of observing that I did it correctly, given I have done the action such that S2 occurs under the observation of O1 and the goal of O1. So this is essentially my loss of doing it correctly or incorrectly, actually. Yeah? And these are my costs of changing my prior density of just having observed O1. And given the context here, I didn't put this also in the conditional here yet, still. Yeah? So to be a little bit briefer here. The prior compared to the posterior that I have optimized my densities, my belief densities, my posterior overaction to maximize the likelihood that I will do it correctly, but having the effort to do it correctly. So these two terms play out essentially and are deciding what I'm going to do. And when I have done a trial, I basically can optimize still my contextual posterior that is essentially nothing else as the loss that I have which is the objective function, is basically a loss, minimizing a loss that I have experienced in the trial, plus the cost of really changing the contextual posterior, the C density itself, right? And if I would do it, and we do this also on the long-term objective, so I have like, we first train the model that it basically sees, yeah, you speak out the word typically, yeah? And so you build like a large prior context that if I see a word, I say it, yeah? And that's the long-term objective basically that builds contextual templates and default parameterizations of these templates. And as a result, within one trial, you basically get the following dynamics unfolding due to this objective function that is being optimized. Yeah? You basically have the equation, the goal loss to do it right. The more you are thinking, the lower the loss, the more likely it is that you get it right. Yeah? So the less likely it is that you get it wrong. Yeah? So the more certain you are you get it right. Yeah, but you have the cost, the sampling of improving your action posterior costs you and gets exponentially more costly. Yeah, this is the red term essentially, and either right, and that the sampling gets more costly in all the cases, and depending on the reward, right? If it's low reward, so if it's not so important to you to do it right, then the costs of getting it wrong are smaller from the beginning or larger, and so that basically plays out. You can do the sampling, so you essentially do a Markov chain Monte Carlo rollouts on your model, yeah? Like essentially within here, right? You perceive the stimulus, and you do rollouts. Well, if I was do action 1, then what would I believe my sampling says? Will I do it right or wrong? And I basically do a rejection kind of sampling, seeing the goal that I want to achieve, so I accept only those that adhere to my goal density with the likelihoods, and then I basically do that sampling, yeah? And as a result, we can show that the sampling process, the decision when I press, you can monitor the sampling and see the improvement over time with these two loss components locally calculated, and then just decide when you don't get any better, when you basically, the profit of doing more sampling is not more valuable than the gain that you get to do it more correct. Yeah? And we can show that the sampling process approximates this sampling process which gets these results, these when presses individual trials, is basically coincides nearly perfectly with the closed form optimal solution. Yeah? So that says basically that if we have this contextualization and well-structured graphical model, basically we don't need to compute in our heads the closed form solution to act optimally, but we just do it by sampling and monitor the sampling process, and that does approximate the optimal solution without calculating it, huh? Which is rather nice and valuable, right? And if we compare this now to human data, so we have here the congruency effect, right? In incongruent trials are peer, congruent trials are peer, so you're of course faster when the word is written in says the word of the color, yeah? But then we have the proportional congruency effect here also as a typical kind of stylized human performance measure. Mostly congruent trials, the incongruency effect is much larger, right? Because only rarely incongruent, so you're not ready to deal with the incongruency, so it's larger, and here it's smaller. And that effect we get with our model as well, but only when we have that contextual inference, right? That retrospective contextual inference that adapts this internal latent contextual state. And what is more is basically only when we have this contextual inference and this context representation that allows me to adapt my priors of just reacting to the word or saying out the color, I have the best energy performance. I have the least cognitive effort over time if there are these regularities like proportional congruency regularities, for example. So that is for me a very big evidence that there is something truth to this, yeah? But of course, there are still many questions open. But what I have shown you so far is basically that habits and planning go hand in hand. Yeah? When facing a task, I'm saying like our contextual frame essentially is a graphical model that is activated. Yeah? And this graphical model parameterizes and predisposes processing priors. The readiness to process a stimulus, the habitual behavior to interact with the world given that stimulus, task routes and relevant world knowledge in general, and also goals that essentially translate into information theoretic priors, right, of doing something, getting it right, for example, right, or getting water into my mouth or something like this. Yeah? And while doing then the task, when I have set this prior, I'm essentially think in this task, in this contextual frame, the context initializes the habits and the action choice priors. Then Markov chain Monte Carlo rollouts yield planning-informed action choice posteriors. Then I execute the action, perceive the result, and I optimize my contextual priors and leading contextual posteriors. And that goes over time and optimizes the system, the cognitive system, over time continuously. Yeah. But now, of course, well, how do we infer these contextual frames now? Now, I mean, in this experiment, I just have given the contextual frame. Yeah, haha. So, but I have optimized the parameterizations of the contextual frame, right? And that how is, of course, a much harder question, where these contextual frames come from. And so I want to lead you to what I find a fascinating challenge. These days, also Cameron Buckner talked about it yesterday and emphasized that that's a nice challenge. It's this ARC challenge, this abstraction and reasoning corpus challenge. Now, second round, AGI 2, 700,000 grand prize. François Chollet came up with this in his famous paper, or in his paper from 2019. A wonderful challenge that I want to show you a couple of things. What this is about. This is ARC AGI 1, the simpler version, one of the simple problems. So you always have matrices, and you show the before-after situation, before, after, before, after. Yeah, and you have to find the principle, right? What's the rule? So if I show you this, what's the after matrix, right? So here, most of you have probably noticed already, okay, the things fall down pixel-wise. That's rather easy, right? Another example of such an AGI1 challenge is here, okay, it's gray on the left, blue squares and red lines, basically 3 pixel lines on the right, so we have to somewhat arrange these shapes and distribute them, right? So that's still rather easy, it seems, yeah? But here's ARC AGI 2 now, so this is what they came up for this year, and this basically, okay, is a little bit harder, yeah? If you compare before and after, you see, okay, yeah, if you take a little time, right, so recoloring is going on here, right? Some rule to recolor something green, yellow, red, blue. Wait a minute, here's green, yellow, red, and blue. Well, why is this one blue? Oh, it has also 2 holes. Oh, this one has 2 holes too. 3 holes, 3 holes, 1 hole, 1 hole. So we have the rule, yeah? So, ta-da, I've solved it, yeah? I hope most of you could follow, right? So that's the rule, but if I wouldn't have moved you through it, right, it would have been harder for you, most likely, yeah? So it's basically a number of rules, so you have this rule set. And notice the generalization that they put in here. Suddenly the rule is not found on top or the top left, but actually here on the right side suddenly, and there are different number of holes, and suddenly the 0 hole one just needs to disappear because those that are not given the rule, they disappear in the output. Yeah, so it's a rather hard task, you see, and there are a couple of others. Yeah, you connect things by connectors, or you move blocks to the left or right, depending on their frame color, for example, and they behave like solid objects, so they have, and there are hundreds of more like this. And now the question is like, okay, why does he show this to me? Why? And the reason is because current LLMs, current O3, GPT-5, and so forth, they suck at it. They're super bad, yeah? They fail completely, yeah? We have the current leaderboard. This is from 2 days ago. This is ARC AGI 1 with a circle. Here we moved up to about 50% with reasonable compute time. Here's the $1 mark. If you go to $100, okay, O3 preview, per task, right? If you invest $100 of energy, yeah, in one task. Okay, then it can solve 80% of these problems, or 70%. Yeah, okay. Is that interesting? I don't think so. Yeah, but fine. Yeah, but notice at AGI2, yeah, the triangles, they are down here. Here. The best one is here. Is 15%. Of all AGI, of all large language models, of all the best stuff that we have out there, they have tried. They have invested $1,000 actually per task to run O3 on this and so forth. To reach nearly 85% last year on O1. And on the ARC AGI2 challenge is nothing. We go here, even look, they had O3 preview. They invested $200 per task. And the system is on below 10% performance. How is that possible? Why are they so bad? And the question I want to ask first is, well, human performance is up there. We can debate a little bit, okay, how good is human performance? Average M-Turkers on ARC AGI1 are about here, but if you have a human panel that is trained to solve this task, they get them right. And I don't know how they put the financing here. I don't think it's the brain energy that was spent to solve the tasks, but it was more the energy to get the people to do it for so many hours, probably to work on them. But right, it's not the brain energy, right? The brain energy is probably more, I don't know, here, maybe, or I don't know, from food-wise or so. Huh? Yeah, that's what I'm saying. It was the cost to get the participants, right? So it's not the brain energy, right? Brain energy is even much lower, right? So what is going on, right? So I want to point out that how do we solve these ARC tasks? I want to say basically, well, we build a contextual frame. We seem to infer the contextual frame, what is going in this ARC task, and then we solve the task by focusing and inferring the contextual frame and thinking within. What do I mean about this? When facing a current task, right, we infer relevancies, schemas of relevant properties. Like I said to you before, there was a recoloring going on. Oh, there are holes. The holes seem to matter. Schemas. Entities are identified, these objects, right? Eventive interactions, recoloring, and a particular schematic systematicity, right? So there's a domain-specific language that we are inferring by seeing the contextual structure, and we infer a chains of thought. I first have to count the holes. I have to see what's the recoloring of this hole, and now the holes gets recolored this, it's going to get recolored like this, so forth, right? So we build a domain-specific and chains of thought. This is our contextual frame that we infer by analyzing these trial-by-trial problems, and then we apply them. When facing a current trial, we instantiate the chain of thoughts, and we essentially optimize our behavior locally. We have Monte Carlo, Markov chain Monte Carlo Markov chains, and we execute the chain of behaviors essentially to then generate the output matrix from the input matrix, right? And why is the ARC challenge relatively easy for humans? Well, the ARC challenge is about real-world problems in the end. Why is this about real-world problems? That's my conviction also, right? And why I find it so fascinating. Learn the transition from a before image to an after or a target image. If I'm thirsty, right, my after image is to get some fluid into my mouth, right? And my before image is, well, the bottle is rather close, right? So why don't I play out my bottle drinking schema, right? So that's something very usual that we have. If I would give you a real-world ARC challenge, right, I could show you like a small group of people in front of a car, and those people sitting in the car. I could show you one or two images, basically, and then I show you a totally different car, a different number of people, as long as they fit, right? My after images, well, they sit in the car together, right? It's not a problem, right? You can do this with a frame or an empty table with flowers. And after the same set, and that same table set for breakfast with a number of sets equal to the number of chairs. I had this idea sometime last fall, and I thought, okay, great if the LLMs cannot solve this ARC task, so they can at least create me the stimuli, right? So I said basically, okay, So let's see if they can do that, right? So basically a black and white cartoon scene, actually that was from Midjourney, rephrased from Midjourney as suggested to be a better term to ask. So draw me a black and white cartoon scene showcasing a simple wooden table adorned with a vibrant bouquet of flowers. Surrounding it are 4 inviting chairs, because I wanted a number of chairs to have the set of breakfast sets afterwards. And it's difficult, yeah. I mean, one could certainly play around with it and optimize this and do reinforcement learning and post hoc analysis and maybe automatize it, sure. But out of the box, this stuff doesn't really work. Maybe it works better than last year now, sure, and it will still work. But counting and so forth, we all know, is not such a good skill of large language models. So basically, current established deep learning-based generative models, I would say, well, why don't they solve it? They do not have the ability to focus their contextual frames automatically, right? By text and so forth, I give them context, sure, so there is some contextual abilities there, right? But they don't do this internally. They cannot infer the contextual frames automatically. They do not enforce the development of consistent latent representation. There's no consistency. It's just autoregressive feed-forward stuff. They cannot recurrently reason within their latent spaces, and they do not have any form of true understanding, that is, any internal verifiable causal model. So what is missing is really an interpretal structures under the hood, as we heard in a couple of the philosophical talks before, right? We need active contextual frame inference. That's my strong belief. And we need good inductive learning biases to make concepts, entities, and events explicit. And in the last 5 minutes or so, I just want to give a little bit of a glimpse of the deep learning side that we are working on, so that I can show you that I'm not just fooling around and saying, we need this, yeah, okay, but nobody knows how. I think we don't know how either really fully, yeah, but yeah, Manuel in the audience has done a couple of wonderful studies here. For example, this one where we trained a neural network with individual slots, and these individual slots start to track objects. So you can really look inside the neural network and see, okay, this slot currently tracks this object. This slot currently tracks this object. If I would take it away, it would forget about that object. And you can see in this video that here this snitch ball that's under the cross here, where the cross is the cross says where the system believes the snitch ball is, and the snitch ball is covered first by one cone and then by a second cone, and the snitch ball is still very well known where it is by the model, so it really can track entities over time, and this is fully trained end-to-end from videos. Here, given the background still. The system, with a little bit of an advantage, can also do stuff like violation of expectation. Again, you can look, into the system itself. Now, it's a little bit more complicated. I will not explain everything what you see here, but you see that occluder thing here. Then you basically see the right object and the left object moving. Here on top, you see how much information is taken from the outside and how much is taken from the inside. And this is the location, the belief of the location for these individual slots where the center of the object currently is. And this is a violation of expectation experiment set up, of course, with an artificial situation. So the object that comes from the right moving to the left will disappear. So you will basically see that the object has disappeared now. Now it should reappear on the left, and the system has decided, well, it must just be still behind the occluder because it didn't reappear. And now the occluder falls down, and it basically moves it still to the far back where it could maybe be, and then it believes, okay, it's gone. And if you test this with violation of expectation analysis of the prediction error that the system has, you indeed see 2 violation of expectation errors. One, when the object should reappear after sliding through the occluder, and 2, after it should really reappear when the occluder fell down to the ground. Now, Manu has worked on this phenomenally further with our newest flip model, just an impression which shows this system now tracks individual objects, but it just only looks locally where it believes the object is and samples locally. We are sampling from object patches from the video and generates here this mask. This is now trained in a supervised manner, but in this performance measure that we have looked into, we actually beat with this system, particularly when objects are small and large images, the meta segment anything system as well, with about over 1,000 times fewer parameters, because we just need to look locally into the image, yeah? And don't need to analyze the whole image all the time. Yeah? We also have worked together with Chris and also Johanna, he's here also, on contextualizing event predictive. On contextualizing event predictive, your eye gaze or segmenting really event structures. So this is a slide from Chris that I really liked a lot. So imagine you have this robot arm that first here in simulation of, again, reaches for this object and grasps it, and then basically transport it to the red dot. Yeah? So we can see this rather well. If I have explained it to you in the video, you would also analyze it quickly, right? So there's a reach, grasp, lift, and hold sequence unfolding. And if you choose standard recurrent neural networks, like a gated recurrent neural network, a GRU, you don't really see any segmentation, right? But what you really want, right, to have an explainable latent internal structure, right, you want to have something like this, ideally, as a latent internal code, right? That really distinguishes the different segments. And that is what Chris has developed over time. Here you see the billiard ball situation, a rather simple one, but basically it encodes here the latent state. Our gate load system encodes the direction of the motion of the billiard ball, and on the right it's essentially, you see how it can skip ahead and always expect the next transition. So it segments the events and jumps to the next change in the event, so it doesn't need to think it through, but basically can hop from event to event conceptually. And we have also modeled infant data for this, but as the time is running out and we want to have some time for questions, I want to conclude with this and basically emphasize what have I showed you. Contextual frames alleviate cognitive effort. That's really the main point. Yeah? They save energy and can focus our minds extremely flexibly. Yeah? Contextual frame inference, somewhat technically speaking, a little bit invokes something like an endogenous CPOMDP maybe. Yeah? It's like it's the decision space within which I then think. Yeah? And of course I also need to infer that CPOMDP, within which actual decision making unfolds. This CPOMDP saves energy and can yield human behavior, as I've showed, at least as the first results on this. And artificial systems need to actively contextualize their latent states. It's absolute to solve the ARC challenge, for example. It seems to be totally impossible otherwise, because brute force search or just random creation of programs just doesn't work, as we have seen. Yeah? To generate more human-like adaptive behavior, to avoid subtle and unpredictable errors, and to develop artificial general intelligence, most likely. So social contextual frames I had to kick out in the end because of time reasons, so enable the maintenance of interpersonal, alternative relational perspectives as well. We've done also some work with it. Maybe you see Asya's Achimova's talk this afternoon. And so basically, to really conclude, on the AI side, I'm thinking that implementing actively contextualizing AI is a fully open challenge, but if we face this challenge, if we succeed, we will be one step closer to artificial general intelligence. And I mean this, and I don't think this is like a joke or something, and we should really think about what this means for our world and societies, with all the potential and all the dangers involved. Thank you for the attention.